Okay. I'm really sorry. Like I said, I should probably start sleeping again at night. That would help with a lot of things. But if you didn't see the email that I sent at 4 in the morning last night, I put up a little blurb on grant writing for anybody who chooses to do the grant writing assignment. As I said, it's optional. If you have 10 million things to do already and don't want to deal with it, that's fine. It's just, number one, I think something useful to learn how to do if you're giving any thought to being a PI of your own lab someday. And it could also make life less stressful on finals week because the alternative is take home final. Analyzing a bunch of real data sets that people in the past have told me is kind of nasty, and that's kind of the point because real data sets are seldom easy. So if you do the grant writing, you can get out of most of the final. And as I said in the assignment description, like, you can just kind of view it as an extra credit assignment that if you do it, it will not hurt your grade, and if you do really well on it, it could potentially help you. So, yeah, and I mean, if you have any questions about the assignment, you're welcome to come talk to me. I probably won't be very helpful in terms of giving you potential projects to write about, but I can help you with the statistics, which is primarily what you'll be graded on
Wait,
for the assignment anyway, yeah?
so sorry, I haven't really seen it yet. So the grant writing, you don't give us a data set, like we have to supply our own data set.
Yeah, the question was whether I give data, and basically no. I mean, the idea is that if there's something you're working on in your lab that you could potentially write a grant on, or just some problem that you think you could do in the future. I mean, like I said, I mean, I'm not really qualified to evaluate the biology side, so as long as it isn't something totally ridiculous, specific aim to is to turn lead into gold or something like that, I mean, I'm fine with it. It's the statistical analysis that I'm primarily concerned with. And as I said in the little blur, I mean, you're very welcome to talk to lab mates, PIs, whatever, to get ideas for the project about what you could write about as long as you write it yourself. So, I mean, if anybody wants to discuss possible ideas too, are welcome to come talk to me. I mean, I can try my best to come up with something, but I mean, there just isn't that much bench science stuff that I know, and the stuff that I do know is probably stuff that most of the people in this class would never do, so I'm just not sure how well it would work. Yeah, like I said, feel free to email me or come talk to me if you have any specific questions about it. Anyway, today, as we can see, we're going to discuss two-way ANOVA and interactions. That is, you'll recall from Monday, ANOVA is just kind of a generalization of a t-test in cases where you have three or more different groups rather than just two groups. Or if you want to be more precise with the statistical terminology, that you can use ANOVA to make inferences about the relationship between a quantitative outcome variable and a categorical variable x, where x is something that has several levels. So the example from Monday, we had like GSH levels in several different cell lines, and the categorical variable was the type of platform, whether it was control, vehicle, or treatment. And so two-way ANOVA is just a generalization of ANOVA to cases where you have more than one categorical predictor. That uh, a common approach for this, if you have like a block design experiment, that you have several different blocks and you apply the treatments within each block. That, say, for instance, you have like a treatment injection and a control injection on a group of mice, and you block by letter, so you have like 5 different letters, and within each letter you assign half to the treatment group, half to the control group. And the question is, does the treatment have any effect? Well, it's quite likely that the litter will have some effect as well. So, and in that case, you want to be able to answer the question, is the difference between treatment and control, is the null hypothesis of no difference between treatment and control true given the effect of block? And this is known as two-way ANOVA, or I can't remember what the or is, and it got cut off in my slide. Oh well, we'll just call it two-way ANOVA, I guess. And as you'll recall, the standard ANOVA model is that if observation I belongs to group K, that the value of observation I is equal to the overall mean for the full population plus the offset for group K plus noise. And the null hypothesis of interest is that all the offsets are equal to 0. That is, that every single observation is just equal to the overall mean plus a noise term, implying that the means are the same for all the groups. The alternative is that at least one of these taus is non-zero, implying that that group has a different mean than the other groups. A two-way ANOVA model is when you have two categorical predictors, and if observation I belongs to group J in the first variable and group K in the second variable, then observation I is equal to the overall mean plus the offset for group J with respect to the first variable plus the offset with respect to group K in the second variable. Oh, and yeah, basically the primary hypothesis of interest on the previous slide is that all the taus and betas are equal to 0. In other words, that all of the groups have exactly the same means with respect to these different variables. And you may also be interested in some secondary hypotheses in this case, that the taus alone or the betas alone are equal to 0. That is, you may want to test the null hypothesis that there's no effect of treatment on the mice. In this case, you may not care about the fact that some of the betas are non-zero. In fact, you may expect that there are differences from letter to letter. And if that's the case, you don't care if that's true, but the null hypothesis that you're really interested in, or are the tau 0, is there a difference between the treatment group and the control group? And as I'll show you in a second, it's possible to test that null hypothesis without saying anything about the betas. Also, you could do it the other way around if for some reason you wanted to know if there was no effect of block without caring if there's differences between treatment and control. So, how can you fit a two-way ANOVA model? Well, we can use regression with dummy variables just like we did for one-way ANOVA. That if you have two categorical predictors, x1 and x2, basically you just define two sets of dummy variables, one for each group. That, for instance, in the mouse example that I just gave, you could define one dummy variable to be 1 if the mouse is in the treatment group and 0 if it's in the control group, and then set up another set of dummy variables for letter. The dummy variable 1 is equal to 1 if it's in letter 2 and 0 otherwise. The next dummy variable is equal to 1 if it's in letter 3 and 0 otherwise, and so on down the list. Once again, you don't set up a dummy variable for the first letter because if you did, there would be no unique regression solution. And then you just fit a regression model to these dummy variables to test to see if all the coefficients are equal to 0. Oh, an example for applying two-way ANOVA using a data set that's built into R. This is a data set on the yield of oats that they wanted to see if nitrogen fertilizer had any effect on the yield of oats. That basically they did a block design experiment because quite commonly as agricultural experience, not surprisingly, there's the observations are not going to be independent, that if plot A is right next to plot B, they may be correlated with one another, whereas if plot A and plot F are on different sides of the field, they're less correlated. So basically they split the field up into 6 blocks that were believed to have similar characteristics, and within each block, different quantities of fertilizer were applied to each plot in the block, and you want to test the null hypothesis that yield does not vary according to block or fertilizer. Oh, this data set in R is called oats, and it has 3 variables. Y is the yield, B is the block, which just given a Roman numeral between 1 and 6, and N is the amount of nitrogen fertilizer that was applied. I don't know what the units are. 2 units, 4 units, and 6 units versus a control group of 0 units. And
How is that
hmm?
the 2 units, 4 units? Where is that coded?
This is down at the bottom. N0.2, N0.4, N0.6. So the reference groups here are block 1 and fertilizer weight of 0. And it's basically looking at the output, it's more or less consistent with our intuition. The intercept corresponds to the baseline groups. So the yield, if there's no fertilizer and you're in block 1, it's about 110.75. And if there's fertilizer, the yield increases, not surprisingly. The increase is greater the more fertilizer you use, 19.5, 34.8, and 44. And it looks like block 1 had the highest yields. All the other blocks had lower yields than block 1. And every single one of these differences were statistically significant. So the interpretation of this output is analogous to the interpretation of the one-way ANOVA output. If you want to test the null hypothesis that every single one of these dummy variables is equal to 0, you'd look at the p-value for this F statistic down at the bottom. It's on the order of 10 to the minus 13, very strong evidence against the null hypothesis that all the groups are the same. And in general, in R, if you say LMY twiddle x1 plus x2, that'll do a two-way ANOVA if x1 and x2 are both factors. R is smart enough to convert both of them into dummy variables automatically.
Sorry.
Mm-hmm.
Sorry, another time was. So if the null hypothesis is that they're all the same, why do we get as a result significance for each of the variables?
So the question, well, the null hypothesis is that they're not the same, and each of these t-statistics is basically comparing each of these groups to the baseline group. So the t-statistics for the B's are testing the null hypothesis. There's no difference between B1 in each of these groups, and the t-statistics for the N's are testing the null hypothesis of no difference between 0 fertilizer and each of those quantities of fertilizer. So all of those t-statistics are significant, indicating that every one of the B's has a lower yield than B1, and every quantity of fertilizer has a greater yield than using no fertilizer at all. Does that make sense? Okay. Oh, the way we interpret it, I guess I just went over, is that if you want to find the mean in the particular group, you add two different coefficients to the baseline. That if you want to find the average yield of plants in block 3 that had fertilized, that got 0.4 units of fertilizer, you take the intercept, which is 110.75, minus the coefficient for block 3, which is 39.42, plus the coefficient for the 0.4 unit treatment, which is 34.83, you get an average yield of 106.16. And what if we wanted to consider some other hypotheses that say we want to test the null hypothesis that there's no effect of block after taking fertilizer into account, that once fertilizer is included in the model, can we reject the null hypothesis that the coefficients, that all the coefficients for block are equal to 0. Now, I mean, in this case, that's fairly obvious that null hypothesis is false, just eyeballing the output, but it's not always necessarily going to be that obvious. And if you just do the summary.lm output in R, that'll give you the t-test for testing the null hypothesis that a coefficient for each particular dummy variable is equal to 0, but that's not necessarily what we want. What we want is the null hypothesis that they're all equal to 0 simultaneously. In this case, I mean every single one of those dummy variables has a tiny p-value. It's safe to reject. You can probably safely reject that null hypothesis just by eyeballing it, but say you looked at these 6 tests and none of them were significant except for one of them that had a p-value of like 0.01 or something. I mean, is that better than you would expect to see by chance? It's hard to say, so it would be nice if there were some more rigorous way to test that particular null hypothesis that one given set of variables are all simultaneously equal to 0. And it turns out that there is, as you'll recall, this AOV command that we used to that we used with the 2-key HSD command on Monday. You can also use for this particular hypothesis that if you say summary AOV and give it the model in your data set, you'll see that it gives an F statistic and p-value for B, an F statistic and p-value for N. In other words, the p-value for testing the null hypothesis that all of the coefficients for B are equal to 0 simultaneously is about 10 to the minus 8, and that for all the coefficients for N are simultaneously equal to 0 is 4.2 times 10 to the minus 11. In both cases, there is very strong evidence that not all of these dummy variables are equal to 0. In general, if you say AOV y twiddle x1 plus x2, that'll give you a ANOVA style output for regression or ANOVA model that, rather than testing a null hypothesis that each particular dummy variable is equal to 0, it tests the null hypothesis that all the dummy variables for a particular category are equal to 0 simultaneously. And let's say that we want to do some pairwise comparisons, that we want to compare the yields of the various fertilizer levels across all the blocks. We don't care about comparing the blocks to one another. We just want to say, ignoring the effect of block, can we be confident that certain different, this is what happens when you don't sleep. Can we be confident that the yields for different fertilizers are different from one another? And turns out that you can do that with the 2-key HSD command as well, that the syntax is the same as before. You give, say, 2-key HSD and give it your AOV model. The only thing that's different is you say which equals n. In this case, we say we want to do all possible pairwise comparisons for fertilizer. We don't care about comparisons with respect to blocks. This basically says what's the difference in yield between 0.2 units and 0 units, correcting for multiple comparisons and taking into account the effect of block. And it tells us that the mean difference between those two groups is 19.5. Gives us upper and lower confidence bounds, and also gives us a p-value for testing the null hypothesis of no difference between these groups. Basically, the way we can interpret this is it's unclear that you get an increase in yield when you go from 0.4 to 0.6 units. I mean, the mean difference is about 9.17, but the 95% confidence interval covers 0, so we fail to reject the null hypothesis of no mean difference between the 0.4 and 0.6 groups. However, we can reject the null hypothesis of no difference between every other possible pair of groups. That 0.2, 0.4, and 0.6 all produce greater yield than 0. 0.4 produces greater yield than, or 0.4 and 0.6 both produce greater yield than 0.2. And in general, if you say 2-key HSD, given an AOV object, then say which equals some variable, then it'll create a set of pairwise confidence intervals for that variable, such that you get 95% coverage for all these intervals combined. If you don't specify which parameter you're interested in, then it'll calculate these intervals for every single variable in the model. In general, you probably don't want that if you don't care about the effect of block. You just want to compare the different levels of fertilizer to one another. If you include block in there, you'll be doing 10 bazillion tests, and you'll have a loss in power to correct for all the tests you perform, so it would be better to specify which variable you care about to reduce the number of comparisons that you're doing. And one issue that can come up in two-way ANOVA models that you don't have to deal with in the one-way models is ANOVA. That basically the ANOVA models that we've considered thus far assume the effect of being in group I in the same variable in the first variable is the same for all groups in the second variable. In other words, in this oats example, if you are in the 0.2 weight fertilizer group, you will have a yield, the difference between the yield in the 0.2 group and the 0 group is about 19.5, regardless of which block you're in. Now, that assumes that the soil's the same in all the blocks. Maybe the fertilizer is more effective in some blocks than others, and in one particular block, the fertilizer doesn't work that well, so you don't get much of an increase in yield, whereas in another block, fertilizer works really well, so you get a big increase in yield. So, and in cases like that, your model isn't fitting precisely as it should, because it just assumes that the effect of being in block I with fertilizer quantity J is just equal to the effect being in block I plus the effect of being in fertilizer group J. If that additivity assumption isn't satisfied, then you may need to add interactions to the model. So this slide here illustrates how you can have some interactions. This is just some figures that I pulled off the internet somewhere. say in this variable we're measuring the mean quantity of something in 3 different regions, east, west, and south, and you're also looking at the effect of gender. In the first slide, there's no effect of region or gender, that regardless of whether you're male or female or what region you're in, the mean value is the same. In this corner, there's an effect of both gender and region, that women have a slightly higher mean than men, and West has a slightly higher mean than either of the other 2 regions, but this additivity assumption is satisfied, that if you want to find the mean for women in the East region, you can take the mean for East region plus the mean for women, and that will give you the right number. Here's an example where it's effect of gender but not region, or an effect of region, not gender. You see there's a difference between the 2 lines here, but the line doesn't differ from left to right. Here the line differs from left to right. There's no difference between the 2 lines. Now, here's an example of an interaction effect, that if you're in the East group, then women have a slightly higher mean than men. If you're in the West group, both groups have a higher mean. Women are still higher than men. But in the South group, men are lower and women are higher. And there's another example of an interaction over here. But here, your additivity assumption wouldn't be satisfied. If you tried to figure out the mean for men in the South group by taking the mean of the South group plus the mean of men, you would get the wrong number, because for men the pattern is different in the South group than it is for women. Oh, the formal mathematical model for it is if observation I is in group J and the second variable in group K and the second variable, then you add yet another offset to the model, that you say the observation I is equal to the overall mean plus the offset for group J plus the offset for group K plus the interaction between groups J and K plus noise. And basically what this is saying here is that if you're in group J with respect to the first variable and group K with respect to the second variable, then your mean difference is different than what you would expect just based on the 2 groups alone. So, for instance, if the fertilizer is more effective in one block than the other block, then this interaction term would be non-zero to adjust for that fact. And just a little terminology thing, when you have these interactions between the model, then the coefficients for the individual groups are known as main effects. And to fit a 2-way ANOVA model with interactions, it's a simple generalization of what we've done already, that basically you just create another set of dummy variables that are equal to 1 if an observation is in group JK and 0 otherwise, and then you can use regression test the null hypothesis that all of the interaction terms have a coefficient of 0, or you could also do these hypotheses about individual interaction terms. And before you just mindlessly stick interactions into your model, you may want to use this command in R called interaction.plot, which basically creates graphs like you saw in the previous slides. You can try to visualize if there's any sort of interactions. I'll show you here in a second. That basically interaction.plot of x1, x2, y, that plots the outcome variable y versus a predictor variable x1 for each possible level of x2. And these plots are useful for identifying interactions, as I'll show you here in a second. Here's the interaction plot for the oats data set, that basically the y-axis here is the yield of the oats, the x-axis here is the amount of fertilizer that the plant receives, and it plots the relationship between fertilizer and yield for each possible block. And what we see is consistent with what we saw in our other model. Block 1 consistently has higher yield than any of the other blocks, and the yield increases more or less linearly with the amount of fertilizer. And if there's no interactions, we would expect all these lines to be parallel. That is, that the effect of having a certain amount of fertilizer in a certain block is just equal to the coefficient for that block plus the coefficient for that amount of fertilizer. I mean, they're not perfectly parallel. They never will be with real data sets, so they're pretty close. So just eyeballing this, you would probably say there's no interactions here, because it doesn't look like the effect of fertilizer, it differs that much from block to block. And there's a little bit of indication that block, it looks like this is block 3, that you don't get an increase from 0.4 to 0.6 where you may get it in some of the other blocks, but if there's an effect here, it's a very small one. And if you fit this model in R, it more or less confirms that. The notation in R is we say the yield is equal to the block plus the amount of fertilizer plus B colon N. That says an interaction between block and fertilizer. It gives us coefficients for every possible block combined with every possible fertilizer level, accepting the baseline groups. And the fact that pretty much none of these is statistically significant is a tip-off that there's no interactions here, and we can safely leave those out of the model. And if you want to be absolutely sure that there's no interactions here, oh well, I'm skipping ahead of myself. In general, if you say y twiddle x1 plus x2 plus x1 colon x2, that'll fit a two-way ANOVA model with main effects for x1 and x2 plus an interaction between the two variables. And if you go y twiddle x1 star x2 star, then that tells R to include main effects and all possible interactions in the model. So that saves you having to do x1 colon x2. If you just say x1 star x2, that includes all the interactions automatically. And if you want to formally test the null hypothesis that all the interactions are equal to 0, you can use the AOV command again. Here I use the shortcut from the previous slide. They go AOV y twiddle b star n, say include the interactions. As we saw before, the main effects for both b and n are strongly significant, but p-value for the interaction 0.97 definitely fail to reject the null hypothesis that all the interactions are equal to 0. We conclude there's probably no interactions in this model. Just to show you what it looks like if there were interactions, this is another data set that's built into R. This is on cabbage weight. We want to see if the type of cabbage and the date that the cabbage was grown have any effect on the head weight of the cabbage, and if there is any interactions. So we compare, so in this case, the two predictor variables are the type of cabbage and the date they were grown. The dates, in this case, are 20 and 21 in a baseline. I forget what the baseline is. And the cultivation type, in this case, is called cabbage 52. I don't know what that means exactly. But it looks like the mean weight of the cabbage in the baseline group is about 3.03. it looks like the weight of C52 is significantly smaller than the weight of the baseline group, and it also looks like cabbage grown on day 21 tend to be smaller than cabbage grown on the baseline day. We don't see a difference between the baseline and day 20. And we find the two main effects are significant when we don't include the interactions. Now let's say we include the interactions that of cabbage type plus date plus an interaction between the two. And in this case, note that now that we've included the interactions, the main effect of date is no longer significant, and one of the interactions is significant. What this tells us is that if it's cabbage type 52 grown on day 20, then it's significantly higher than the baseline group. A cabbage type 52 grown on day 21, no noticeable difference between that and the baseline. And with the exception of cabbage type 52, the cabbage grown on days 20 and 21 were not significantly different from the baseline. And although despite that fact, if we do the ANOVA model, it says both the main effects and the interactions are significant. So the date has some effect on the head weight, as does the type of cabbage, but there's also an interaction between the two. And here's an interaction plot to try to give us a better idea of what's going on, and it's roughly consistent with what we saw in the regression output. For day 16 and day 21, there's not much in the way of an interaction going on. That the cabbage are consistently larger for day 16 than they are for day 21, and the cabbage in group of type C39 are consistently larger than the cabbage of type C52. However, things get a little more interesting for group D20, or for day D20. On day 20, group cabbage type C39 has a reasonably large weight, but whereas for the other two days, cabbage C52 is smaller, C52 is actually slightly larger on day 20 in C52. So that's an example of an interaction that the head weight for having cabbage type 52 grown on day 20 is different than what you would expect if you just took the mean for the effect of cabbage type 52 plus the mean of the effect of being grown on day 20. So the way that one can interpret this looks like cabbage type C52 is associated with a lower head weight than C39, except on day D20 when it's associated with a slightly larger head weight. We can figure that out by looking at the picture, but that isn't necessarily obvious if you look at the output from LM, because the terms that end up being called significant depend very heavily on what group you designate as the baseline, and that's arbitrary in many cases. So you should always look at the ANOVA output rather than the individual t-tests from LM, and probably plot the interactions as well. So, things to remember for today's lecture is that if you have more than one categorical predictor, you can still do ANOVA, and sometimes you need to include interaction variables in the model if values of one variable vary depending on values of the other variable, and be careful how you interpret these multivariate ANOVA with interactions, draw the pictures and so forth to try to wrap your head about around what's going on. New R commands for today is if you go lm y twiddle x1 plus x2, it gives you two-way ANOVA. If you put in a star, that will give you interactions. And you can also get the AOV style output if you want to test the null hypothesis that everything's equal to 0 simultaneously, and interaction.plot to visualize interactions. Any questions about any of this? Start late and finish almost exactly on time. That works, I guess. Okay. Friday, hopefully I will be on time because I have a meeting before this, which kind of forces me to be.